Today, we'll bridge the gap between the classical and the quantum worlds with the powerful WKB method. Here, the wave function is interpreted in terms of a classical path with quantum effects appearing as phase factors and amplitude modulations along these paths. As such, this is known as the semi-classical approximation. And in today, what we'll cover is actually two questions in one video. One that's an example of the approximation, the other is a derivation of it, and we'll get to see how all the inner workings come out. And this would be in Chapter 9 of Griffith's third edition. And to start, we're told to use the WKB approximation to find the allowed energies En of an infinite square well with a quote shelf of height V0 extending halfway across. Figure 7.3, which we'll see in a sec. Okay, so shelf, 0, and infinite otherwise. And then we're tasked with expressing your answer in terms of V0, En0, which is just the ground state, the nth allowed, or the zeroth order energy for N for the infinite square well, and then assume that E zeroth order 1 is greater than V0, but do not assume that En is much greater than V0. Compare your results with the answer we got in section 7.12 using the first order perturbation theory. Note that they are in agreement if either V0 is very small, the perturbation theory regime, or if N is very large, the WKB semi-classical regime. Cool. Before we get to 9.2, let's get a reason why we like this. Well, clearly we're trying to link the classical and quantum worlds together. And this is done because some aspects of the trajectories are actually modulated or vary with spatial dependence. And that's what the phase factors and amplitude modulations are that we talked about immediately. But here we have a challenge, and this will become a very big challenge for us in this whole chapter. Where does the WKB break down? Think about that as we're going through this, and as you may have seen from the diagram initially, you'll see exactly what that is. That being said, the PDFs, both will be available. Just comment PDF on the video and I could send you the link or something like that. For whatever reason, the link sharing has been weird lately, so let me know if you want it and glad to share it with you. You can have them for your collections. But with that, let's get on to part 2 of this video so we can see what we're dealing with now that we see the example. Let's get on to one that is a derivation. Now, this is a derivation that uses more of a power series approach, so it's more of if you study differential equations, think about power series solutions, method of Frobenius, things like that. Let that come into your mind as we get into this. And so and then this question just says, starting with this, here's the form that we want from the free particle. This is our motivating factor. How can we get there? Okay, well, let's see that if we play this game, we plug it in, we get this equation, use a power series, but this time we're expanding in terms of h bar instead of some other function like x or variable like x. And then we'll group them together in terms of like powers for h, so the separate orders. And then we're going to recover everything. And here's a little math note if you want it, but the bigger point that I wanted to touch on with this particular problem is that the WKB and perturbation are complementary techniques in quantum mechanics. Each are suited for different types of problems. And here, the WKB method is best for slowly varying potentials and provides a semi-classical approximation, which we've touched on, while perturbation theory is effective for small perturbation in an otherwise exactly solvable system. Okay, so in some of these systems, we might not have a differential equation that's easy to solve at all. Okay, so understanding both methods allows for a broad range of approximations, which we clearly have seen the need for as we get more dense into the theory. Not everything is a nice infinite square well or a simple harmonic oscillator, and we'll see how those things combine here shortly. But enough of this rambling with the background. Let's get in and get our hands dirty with this method and see how well we understand it. I certainly am still struggling with it even after years later. But still, very fun method. All right. So we were told that this was a potential that had a shelf. And this is what we're looking at from figure 7.3. And we see that it's piecewise defined. So from 0 to a over half, or a over 2, so half the well, we're at v0. And here we're at 0 for the other half. So because this thing is split up into two piecewise, we also need to go ahead and write the momentum as a piecewise definition too. Now this momentum came courtesy of equation 9.2, where all we did was rewrite the Schrodinger equation in terms of the momentum and then solve for it to where we had the differential operator on the left hand side and the momentum on the right hand side, much like we had done with the energy states to begin with anyways. Now from that we see that for 0 to a over 2 we're stuck with E minus V naught, and then that's fine, we don't know what V naught is, we just have the assumptions on it. And then from there on the second half of the well we saw that V was 0 there, so we're fine. That's going to simplify this, but what we have to realize is that from equation 9.17, which is what's going to help us find what P of X is, and all the fun stuff that comes with that, what we realize is that for a potential well with two vertical walls, this is the quantization condition. And because of that, we have to split up the regime from 0 to A into 0 to A over 2 and A over 2 to A. Okay, and what this is actually measuring is the phase factor phi of x. So if you're following along in the book, there's your equation numbers, but we split them up. Again, none of these vary as position goes along. This is a constant for the whole position it's on, so we can just bring them outside the integral and simplify. Okay, so in doing so, we see that we get both of them cover a distance of a over 2, so half the well. And then both of them had a root 2m all attached to them, so we can just factor that out. And then we see that what we're left with is E minus V naught from the first half, and then E on the second half. Again, all these are common, so we just kind of group them outside. And this is the quantization condition for the infinite square well. Okay, that just tells you that the boundary conditions on this system are what's actually needed. Okay, so from that we can actually quantize this instead of keeping it classical, which allows it to kind of vary in all these weird ways in the continuous, much different world. But from that we still need to solve for this E fella here. So let's go ahead and push all this blue stuff over, and once we do that we see that we get 2 n pi h bar over a times square root of 2m. The reason why the 2 is outside here is because now when we square it, because we got to get E uncovered, so we have to square both sides, we get this gross distribution and squares mixed up. But then we see that we end up with 2 goes to 4, and then we have n squared pi squared h bar squared over 2ma squared. Guess what? That's our 0th order energy levels, which tells us that anything after this is going to be a first or second order addition to the energy level. Okay, and that's what we're going to need when we're comparing this with the perturbation results. Okay, so that's a nice substitution to make there. Now again, because these square roots are here, we have to put this E, that E, and this V naught over to this side over here and square both sides. Once that's done, we see that we get 4e squared minus 4ev naught, all from this thing, and distribution. Cool. That tells us that we need to square the 4e and naught minus 2e plus v naught on this side, and that distribution was gross, so I left it out, but it's in the PDF. And in doing so, we see that this cancels with that clearly with the cross signs, and now we're left with something that just has 16 E naught E, so E is by itself here, so we'll push that over to the other side since they cancel. Beautiful. Now we're left with 16 E in with the 0 order, and then all the transcending terms. We put these terms in that order for a reason, because then we can divide all the 16 E n naught or E n to the 0th power to every term there. We see that 16 and 16 cancel. One factor this cancels, leaving us with the 0 order here. Then we see that 8en with the 0 cancels, but leaves a 2 there. Makes sense. And then this one has nothing to cancel with, so it just sits on the bottom. this is the actual answer that we have using the WKB method. Okay. Now, what this differs is that in the perturbation theory via the example 7.1, we got En equals En to the 0, so the 0th order, plus the V0 over 2. So we got this thing. But this is what occurs in the WKB method. And this can be accounted for because we notice that if the potential V0 is very small, right, then that will, being a square, will go to 0 pretty quickly. Or since En is approximately on the order of n squared, which we can see up here, we know that if n is large, that's what's going to get rid of the second term. So we actually match exactly what we need it to. And it's actually important to us because if V0 is small, that's more the perturbation theory route. But if n is large, that's more the WKB route. So here's a nice meshing of the two. Okay. Now, there's still a lot of questions about this. This is a cute little example, and the only real thing we needed was the quantization condition. But how do we come about these equations in the first place? And that's what's going to bring us straight to 9.2, which we will see now. So, how did we even get to these equations in the first place? Well, amongst the derivation of it all, we hypothesize that, well, if we're somewhere over here, then we're approximately exponential as we go into a turning point. As we go out, then we're approximately sinusoidal based on the energy levels. Are we E greater than V or are we E less than V? And that's what kind of deteriorates or determines, not deteriorates, what we use in the approximations. But nonetheless, we know that sinusoidals or trig functions can come from exponentials too, so we start with the concept that the function needs to take the form of e to the I with f of x of some sort. But notice here that we have the exponential of ih bar. Again, if we go back to chapter 6, this ih bar was the highlight to what was in the quantum world. And as we saw, it was kind of the quote generators of multiple things, as in angular momentum was the generator of rotations, things like that, okay? And so what we need to do is kind of follow that motto here because it's been working for us, and who doesn't like a good exponential, especially in differential equations? So we use this theory, or we use the setup here, and we plug it into the Schrodinger equation in the form of the momentum instead of the energy. And now we could see that we're going to have two derivatives. So the left-hand side, where we're taking a double derivative, we end up with this via chain rule, and then again with product rule. So we get a double prime here on the function inside, which is yet to be determined. We have to find that. And then f prime here is squared. Okay, that comes from the chain rule acting on it twice. But nonetheless, what we can do is now we have our left-hand side. Now we can put this together with the right-hand side, again, with respect to momentum here. So we're fine. And in doing so, the exponentials on both sides cancel. Beautiful. Love it. Then because we had an h bar squared over here, one of those cancels with one of these, and we get a nice simplification. So we're going to go ahead and distribute this I into the bracket. So I f double prime. Now this goes to I squared, which we know will go to -1 here soon. But I'm still left with the negative p squared over h bar. So let's go ahead and multiply this h bar over. I h bar double prime plus now we have a -1 here. H bar and h bar cancel. And we're left with a prime squared, and that's equal to negative p squared. Add that over, and we get the exact equation we want. Now, of course, this is a second order differential equation, linear, all that stuff. We knew it should have been linear because we're dealing with the one-dimensional equation here. And with that, this is where we can use power series to actually solve this equation and find out what this f of x should be to begin with. Let's see how we do that. So this is part B of 9.2, and if we're running with the power series solution, what we see immediately is that we have several orders. And of course, normally power series, you go up in order, but then you go up to n order, divide by n factorial. We saw that back from Calc 2 and all that fun stuff. But here, what we see is that we have h bar squared without the 2 because eventually they're just going to cancel anyways. Trust the process, let it run through. We have the same statement with the derivative, second derivative. Now here's where you have to be careful, and maybe something like Mathematica can help you. When you're doing a power series expansion and then you have to square the series, you have to regroup everything in terms of first order. So f prime here needs to be distributed into this and this because we only care up to the second order. So we have f prime distributed to itself, f prime distributed to the green, and f prime distributed to the or to the function 2 rather. I'm color coordinating, so I'm calling them 1s, 2s, things like that. And it's so you keep doing this until you get up to everything that matches with h bar squared, and then we just cut off the series. And that's where something like Mathematica would be able to help you. Or if you just want to be a brute about it, you could, see that if I distribute this, this, and this, h3 don't care about, then this to this, I can only do, one of them. But because then I'm going to end up with h bar and h bar squared, that gives me h bar cubed. Don't need it. So we see that we're left with this stuff here. All right, so all of that now coming back together. If we plug this back into what we had, the differential equation we just put together in part A, we see that we get the square here with an IH bar, and pay very close attention to the fact that that's an H bar. That's going to ruin the order terms that we have if we don't pay attention to it. Don't just blindly put it into that position without distributing the IH bar. And then here we just have the squared, the second or first derivative squared running by itself, so we're fine. And then of course our p squared here. And when we go ahead and distribute that and recast this in the new colors, we'll see exactly what the orders are. Okay, so as promised, distribute that IH bar. We see that that first term now goes to a, instead of a 0 term, we go to a first order. That second term goes from a first order to a second order. And then we have a third order here that we do not need to worry about because we're only concerned up to the second order. And then the first derivative squared gets put together here. Notice that p, however, was of the 0th order since there was no h bar there. And of course, since all these are equal to 0, if we group them together by their orders, what this tells us is that the 0th order, everything in the 0th order needs to be equal to 0, 2. And that's where we get that the negative sign here needs to be equal to that. So we get this equation, green and green. Take out the h bars because they cancel with 0 anyways. And then we're left with that equation and the second order to this equation. And that's what we were tasked with doing now. And from these equations, we could solve for f prime and f double prime and all those other fun stuff. But first, what this allows us to do is to solve for f naught and f1, which is needed in the original series expansion to begin with. So we can solve for f0 of x with the 0th order equation. So we see 0 here, one derivative. In the first order, we have a 0, 0, 1. So we could clearly get the 1 from this one. And then here we have a 2, but we don't need it since it's second order. So that's fine there. From there, we go ahead and see that f prime of 0 squared is equal to p squared. So take the square root of both sides. Just make sure to keep your plus or minus with you. From there, we see that the prime just means that we had a derivative. So we put it in derivative notation, make it explicitly clear. And that from there, we can go ahead and take the square root or the integral of both sides to get this f0 uncovered. And we see that f0 is equal to plus or minus the momentum function plus some constant. Easy enough. Not bad at all. But because we have 0 and 0 put together in the first order, we need both of these 0 functions to go and solve for the 1 function. So let's go ahead and utilize this result in the next page. So, like I said, to solve for f1, we need the first order equation. And we see it set up here. But clearly with the function 0, we need to solve for the function 1. And in doing so, we push everything over. So I is now over 2. And we have a double prime over the single prime here. And in doing so, what we see is that d by dx, or we can rewrite this double prime as d by dx of f prime of 0. And we showed that f prime of 0 was equal to plus or minus p. So the derivative acting on plus or minus p gives us p prime here, like we see here, and the plus or minus signs will cancel, so we're good there. And now we have a differential equation with just f1 and p's, but we realize that a derivative over itself is exactly what the derivative of a natural log is. So a nice little, if you want, you could even use an integration factor to prove that. But that's just a nice little, hey, let's make our lives easy and use this insight now to save ourselves trouble later. So with that, what we see is that we have d by dx on both sides, integrate both of them, and we'll be good via the fundamental theorem, except now we just have to account for another constant. So we're good there, we're happy there, and now from this, we can put f0 and f1 together into one equation and actually solve for the 𝑊𝐾B equation itself. So remember, these functions came from a power series. So now we have to put them back together. And since we have f0 and f1, those are the first two things in the power series. Okay. So putting these back together, then we have plus or minus px dx with the integral, of course, and the first constant. Now we have to put on the h bar here because that was the expansion that we chose. And this is f1 here. Okay, but again, h bar being multiplied into another constant, it's just a constant. So C1, C2 combine to give us K. Constants are constants. We can solve for them later. They're almost the bookkeeping or sweeping under the rug of math. And now we see plus and minus again. Everything's nice and compact here. But this is the function that we need to actually put into the wave function. That was the argument of the exponential. Okay. Now that we have this wave function here, we can just use some algebra and actually split up this exponential with some clever tricks and make our lives easy. First thing we got to do is distribute this I over h bar and then clean it up. So distributing the IH bar, we get something on the integral, cool. IH bar on this second term, well guess what? They canceled. And the I squared turns this plus sign to a minus. So we're good to go there. And of course, distributing that to the k just makes us a new constant, k1. So we're good to go. And now we can use the power rule for logs, put this negative 1/2 up top, putting that as a plus sign there, negative there, good to go. Now if we split up this exponential, because anything addition in the argument leads to multiplication of the functions, so we see that the e and ln cancel, leaving us with px to the negative 1/2, and of course it has to be multiplied. And then we have e to the k1, which is just another constant, big C. Cool. And this leads us straight to equation 9.10, which is the 𝑊𝐾B equation for this approximation scheme, where we have C over square root of the momentum, E plus or minus IH bar integral px dx. Now what's interesting here is that this exponential here is actually the form of the integration factor if you've taken differential equations. So this is kind of making sense now. And so linear equations, we like them, we want to deal with them. Certain regions where they work, we're going to see very, very quickly when we get to the connecting equations how messy this is going to become. So let's take this while we can and have fun with it. But with that, this has been a really fun journey to kind of dive into a new method, and let's see what we can do moving forward. Okay. So in summary, again, thank you for watching. I could not put either one of those into one single video. So seeing an example and then working through a derivation on why these equations existed was important, both in time efficiency and just to keep the conceptual bridging put together. That being said, in looking for some pictures of this, I found a couple nice references, which I will go ahead and try to link below. If not, I'll make a post on the Patreon if you want them. But there's going to be a lot of crossover between this and verifying with perturbation theory, things of that nature. So definitely be on the lookout for some random links here or there because there's a lot to try to put together in this system. That being said, again, Thank you to supporters who keep sharing, liking, and commenting. Um, the algorithm thing is weird, but I think for those who actually like physics, you're going to find a way to talk about it regardless of the algorithm. So, thank you to everybody who's reached out, especially going into this new chapter. It's a lot of fun. And if you'd like to support, you can become a patron or donate through Buy Me a Coffee. Both are very, very helpful, especially with trying to get new resources and books on the run. Been very, very kind. So thank you to everyone. I look forward to seeing what we can come up with next because this theory about to get a little more dense, and this is still laying the groundwork for the actual quantum field theory stuff that we're going to see with action and modifying that action. So hope you're excited because it's going to be a great fall semester. See you at the next one.